Good morning, good afternoon, and good evening. This is a presentation on the Hyperonomy Universal Decentralized Identifier URI Specification and how that grammar compares and contrasts with the did ABNF grammar. My name is Michael Herman and I'm an independent blockchain architect. I live on a ranch in Alberta, Canada. And I thought I might do something a little different here at the beginning and have a pop quiz. So here's the question. You can click pause anytime over the next few seconds to contemplate the answer. And the question is, how many distributed subsystems can you identify in this photo? I hint that there's almost 40. And I'll give you the answers at the end of the talk. So you can click pause now, write down a few of your ideas, and then continue on with this webcast. The purpose of this presentation is to compare and contrast the did-uri-spec grammar from the Hyperonomy Universal Decentralized Identifier URI Specification with the did ABNF grammar from the Decentralized Identifier Specification. And secondly, to document various technical strategies for the two did grammars to coexist, but not only coexist, but being used together in a useful way. The primary audience for this presentation is implementers and maintainers of did parser software that is compliant with the did-uri-spec, including but not limited to the W3C Decentralized Identifier Specification, the did resolution specification, the did resolvers that will be implemented against that specification, as well as, for example, the agent-to-agent communications that's part of the services that are part of the Hyperledger Indy Agent framework. Background and what effectively became a good executive summary for the rest of the presentation is presented in the next couple slides. So let's look at a high level, 4 examples expressed using the did ABNF grammar from the Decentralized Identifier Specification and the did URI-spec grammar from the Hyperonomy specification. So here's 4 examples. This is using the did ABNF grammar. So we have did, which would return a did document. We have did $exam underscore src. And we have below that we have did semicolon exam underscore src. And then at the bottom we have did exclamation point pqrs. So while the first one's fairly obvious, the other 3 are not so obvious what they do. The semantics around number 2 are go and retrieve the did document locally to your client application, and then look in that did document for a fragment that is labeled with $exam underscore src. So the resolution is done on the server, and your application code is expected to do the dereferencing on the client side. Number 3, what we're doing there is using exam underscore src to dereference the service endpoint, get its URI URL for the service endpoint, and then do a substitution into this expression, replacing, in this case, the entire did URL with the value of that URI URL for the service endpoint. So you don't get a did document, you don't get a did document fragment, you're actually getting a URI or a URL. At the bottom, that's for dereferencing content. For example, in a hash link scenario. And this says go out and find the content that's labeled, for example, by PQRS. within that particular resource identified by the did and return that, that content. Here's the 4 corresponding examples, example use cases. And these are defined using the did-uri-spec grammar. So the first one is just simply did, and it obviously is the same or should be the same as the did ABNF grammar. 2, 3, and 4 is where the did-uri-spec differs from the Decentralized Identifier spec. Here we are using exclamation point as the pipe transform character, and in number 2, $select ID is the transform, and it has a parameter exam underscore src. So what we're doing is we're selecting that did document fragment and returning it. And this is all done server-side. There's no client-side interaction as there is in the case of the did ABNF grammar. 3, here, service ID is the meaningful transform, and its parameter is exam, again, underscore src. So if in the previous example 2, we're returning the did document fragment that describes the service ID, in 3, what we're actually doing is that transformation of this entire did URI to whatever the value is of the URI URL for the service endpoint. But when we look at these names, select ID and service ID, it becomes much more obvious what the intended function is. The did URI spec from a semantic and cognitive perspective operates at a higher level. Number 4 was where we're dereferencing a content ID, and so we simply specify content ID equals PQRS, and the corresponding content from the corresponding resource identified or associated with the did would then be returned. Again, just to hint, what the rest of the presentation is also going to talk about is the did-uri-spec, or a parser rather, implementing the did-uri-spec can actually translate any of the did-uri-spec grammar constructs down level into the did ABNF grammar constructs. It's almost like a high-level language like C or C++ or Java or C# being compiled down into an intermediate language. Java bytecode, Microsoft IL, and that'll be the strategy from a coexistence perspective. So there's nothing wrong with the did ABNF grammar for a particular audience, for a particular set of use cases, and it'll be up to developers to make the choice of which one they prefer. Okay, so let's look at the grammars. I'm actually not going to describe them in detail. I'm going to stay on each one for about 5 seconds. If you want to look at the grammars in more detail, click pause. So here's the generic or baseline did URI spec grammar. It's called the generic or baseline because this is the generic grammar that will match all did URI spec did URIs. But there's also, the grammar also supports domain-specific did grammars, which was a subject of the previous 2 webcasts. But this is the baseline. This is the most common generic one. And it is RFC 3986 compliant. Again, the work of the Decentralized Identifiers Working Group community working group is working to, finalize the did ABNF grammar. This is the before Barcelona version, before the recent RWOT event. And this is the after Barcelona ABNF and grammar defined using ABNF notation. This is the one that supports, for example, the exclamation point for content ID dereferencing. It also has some other changes relative to the previous ABNF grammar, did ABNF grammar. So let's look at some in-depth comparisons, some more technical use cases, and look a little bit at the grammars themselves. So these are slides 45 and 46 from the original Hyperonomy universal did-uri-spec. And it identified a series of 20-something what are called high-level user scenarios, did-uri-spec user scenarios. And in terms of doing an apples-to-apples comparison between the did-uri-spec and the did-ABNF grammar, we're just going to look at the first four that are supported, which are supported by each. The did-uri-spec supports all of the other notations below, in addition to these on slide 46. So let's go back and look at each of those four in turn. So here's the four on the left. We've already covered these in the executive summary samples. This is what the did-uri grammar looks like for the class of user scenarios we're looking at here. Again, fairly concise. Previous webcasts have used the term cute, concise, understandable, technically elegant. Let's again just review how the did ABNF specification implements each of these four use cases. So, did to did, not a problem there. This would be did colon, the did method name, registered did method name colon, and then whatever the did method specific form of the identifier is. Here, pipe $select ID, which is going to select a did document fragment, is encoded this way in the did ABNF specification, so you have to know that that's what the pound sign means. Similarly, in number 3 here, service ID $pipe $service ID equals exam_src is equivalent to did semicolon exam src. You'd have to remember that semicolon means that you want a remapped URL. And lastly, we've got this scenario here where pipe $content ID equals PQRS is mapped to did exclamation point PQRS. And you have to remember that that's the semantics associated with PQRS. And then lastly, here's a fragment of the did ABNF specification, the after Barcelona version, that shows you the pound sign, the exclamation, and the dollar dereferencing characters. So let's look at a small table, kind of a feature capability comparison of the two grammars. So the comparisons are broken into 4 high-level categories: extensibility, supported specifications, RFC 3986 compliancy, and and then how is dereferencing performed. So from an extensibility perspective, previous did-uri-spec webcasts have talked a lot about the open to innovation principle. The principle that internet specifications, internet standards need to be open to innovation. Innovations that might succeed, innovations that might fail, TCP/IP and TCP/IP packets being the canonical example. So you've seen through the examples of the did-uri-spec grammar that there's those dollar transformer names, dollar select ID, dollar service ID, dollar content ID. So the grammar does not, the generic grammar does not specify which names are valid. It can be any name. If you want to have more tight control over your grammar and which transformer names are allowed, then you can create a domain-specific did grammar, and it supports the open to innovation principle. The did ABNF specification is very much limited by the number of allowable special characters, and I believe it's using 3 of the only 3 that are available. Even if there's a fourth, it's a severe limitation in terms of other things that you want to do. A severe limitation built on the assumption that you want to do more than is currently defined. But if the way the Decentralized Identifier specification is written, if that's all you ever intend on doing, imagining yourself doing, then that's fine. But it doesn't adhere to the open to innovation principle. Support for domain-specific did grammars. As I've already explained, that's supported by the did-uri-spec. It's not supported by the did ABNF spec. Coexistence with alternative did grammar. So we're going to show in some subsequent slides here and how I explained in the executive summary how these high-level, more descriptive did-uri-spec URIs can be compiled down level and implemented using did ABNF grammar URLs. Through the generic did-uri-spec grammar and specific domain-specific did grammars, the did-uri-spec can support did documents, can support did document collections, more diverse scenarios like Indy protocol discovery and Indy message attachments. The did ABNF specification, its purpose, its role, its goal in life is just supporting did documents. It's not a right or wrong thing, it's just the way that they were targeted when the working group was created. RFC 3986 compliancy, so that is guaranteed by the did-uri-spec and as well as any domain-specific did grammars that you derive from that generic spec. There's still a lot of conversation within the did ABNF community working group with respect to that. An important difference, and it could even be claimed to be a semantic inequivalence. The did ABNF uses the #, and the prevailing discussions indicate that dereferencing of a did document fragment using the # should be done locally, because that's the way that HTTP URLs and HTTP browsers operate. That there needs to be a full did resolution of the did document associated with the did. That needs to be retrieved from the did resolver, and the actual dereferencing through the # would be done locally. So that's entirely client side in terms of the dereferencing operation once you have a did document. On the other hand, the did-uri-spec grammar by default is going to assume that it's being done server-side, that when you ask for, if you use the $select ID transform, you are going to get that did document fragment and just that did document fragment, and that will be returned directly from the resolver. You always have the option of not passing the $select ID transformer and getting the entire did document and performing the dereferencing locally if that's what you choose. Coexistence and migration. So if we go back to the original did-uri-spec webcast, it talked about parsing and processing, and it highlighted a number of pipeline examples. So this is the most common one, where the did-uri comes in, it's parsed. The abstract syntax tree is passed to the analyzer, the semantic analyzer, which is going to annotate that abstract syntax tree, the AST. That can be optionally passed through an optimizer to optimize the sequence of physical operations required to resolve that whatever the did-uri is, either at the document level, but more importantly at a fragment level, or any of the other 20 use cases supported, high-level use cases supported in the did-uri-spec. And then finally, that's given to an execution engine. And this is the sort of the happy path. This is where the resource that's associated with the did is assumed to live in the verifiable data registry. So this could be the Indy ledger, for example. One of the other examples that was talked about in the original did-uri-spec webcast was, did-uris that are used to query or return a document that identifies the protocols or features that are supported by a particular agent. Following the same pattern, there'd be an optimizer and an execution engine that is specific to the agent feature database. For the Indy message attachment scenario, again, this one has an asterisk there. This isn't a totally legitimate scenario because agent messages aren't identified by DIDs, but if they were, it would be exactly the same approach for dereferencing an attachment. And then lastly, there's the use of did-uris in ID attributes, like inside a did document. So those are kind of the four most common scenarios. Let's look at how the did-uri spec would work with the did ABNF spec in cases where you have different kinds of did methods, such as the sovereign did method, the Bitcoin did method, the ERC-725 did method, or the IPFS did method. So if a did-uri comes in, and when I say did-uri, I mean a did-uri that's compatible with the did-uri spec, it would be parsed and analyzed just like before. And it would be optimized as a pure did-uri based AST. And knowing which did method was being targeted, somewhere between the optimizer and the execution engine, that did-uri AST expressed using the did-uri spec grammar would be translated into a did ABNF compliant did URL. So So this allows us from a coexistence experience to actually write on top of, it allows the did-uri-spec, did-uris to write up on top of the did ABNF URLs. If you go back to the very beginning of this webcast, to that executive summary section, where the blue arrows were showing how you go from the did-uri spec-based did-uris down to the did ABNF-based URLs, this is the slide. And so that those did ABNF URLs could then be used to leverage the existing universal did resolver drivers and essentially have the did-uri spec grammar and did-uris compatible with that grammar be able to run transparently and with 100% compatibility on top of the existing family or the updated subsequent updated family of universal did resolver drivers. Over the course of time, though, you want the optimizer, you want a native optimizer and a native execution engine that would go directly against those underlying data stores and not necessarily have to go through the did resolver drivers. So that's what we see in this scenario. Each of those underlying data stores has an API. It's the API that the universal did resolver drivers use. And so over time, the did-uri optimizer would run against the did-uri version of the execution engine. And it would only be at the very bottom sort of physical access level that it would need to tie in to the VDR APIs for each particular did method. I hope that's kind of clear. The previous slide was talking about coexistence, where one is running on top, where one grammar is essentially running on top of the other. And this is a scenario where the did ABNF grammar would no longer be required because the parser and processing pipeline would be running directly against the underlying data stores, the underlying ledgers or DLTs. So wrapping up, the next steps continue to be the same for all 4 webcasts. It's about growing the number of user scenarios, continuing to validate the approach, engage with more and more diverse did communities, more and more higher level scenarios, building and testing the did-ui grammar and the domain-specific did grammars that are created, grow the outreach in terms of awareness, knowledge, and understanding, etc. Which brings us to the quiz. So, how many distributed subsystems can you identify in this photo? The hint is that there's almost 40. Let's briefly look at literally 3 slides full of subsystems. So the air seeder has man-machine sensors, interfaces, alarms, gauges, step ladders for physically crawling up and loading the hopper with seed. Hydraulic lift systems, hydraulic power systems, mechanical systems in terms of controlling the infield soil depth, being able to fold the entire air seeder into a configuration for on-road transport. It has a floating architecture or mechanical design so that if the field is uneven, this 40-foot wide implement continues to, for example, deposit seed at a uniform depth below the surface, even on irregular ground. Part of that is attributed to its multi-sectional structure, and the last component of the mechanical system is it has a hitch for being pulled by a tractor. There's the airflow subsystems, and that airflow is used to carry the seed from the hopper at the back through to each of the individual tines, to each of the individual shovels that are plowing through the ground. Not only seed distribution, but fertilizer distribution as well. There's the whole tires and wheels and hubs and axles and the supports for those axles and the casters, the swivel wheels is another distributed system. There's a ground-driven drive. You want the amount of seed and fertilizer to be deposited at each shovel to be exactly synchronized with the actual ground speed of the implement, of the air seeder. And so on the bottom left-hand corner, actually right next to where I'm standing, is a ground-driven drive that's used to actually synchronize the distribution of seed and fertilizer, and then it's the subsequent delivery of that seed into the ground. So soil management, I use that term to refer to the actual cultivation activity that the shovels perform as they move through the soil, seed delivery into the soil, and then there's a set of devices with large black discs. Those are called packers, and they're used for packing the ground in and around the seed after it's been deposited. Finally, there's a whole lubrication system on the air seeder, conventional grease nipples that have to be filled with grease, and then there's oil that's used for different parts of the hydraulic power in terms of loading the hopper and other things. So so this is the first set, and the numbers in brackets is sort of the number of subsystems within each row. So we see quite a few there. The tractor, there's the diesel power plant, the cooling system, the fuel system, the hydraulic systems, the engine air intake, the cab, tires, wheels, hubs, and axles again, lights and lighting, the drawbar that connects to the hitch, which pulls that implement forward across the ground at a measured speed. And then, of course, the tractor has its own lubrication system for all the moving parts as well as the engine itself. And again, looking in the parentheses, you see there's a very large number of subsystems here. Lastly, and this is one you may not have thought of as you looked at the picture, but when you look at that bright blue Alberta sky, the weather is a complex environmental subsystem that has to be dealt with, in most cases just accommodated. And then there's the soil itself, the nutrients, the moisture, the straw content, the whole husbandry activities related to maintaining the soil quality. So if you add these up, there's about 40. If you got 5 or 10, I would be pleased. And hope you found this to be an interesting experiment. Of course, it's actually a commentary on the complexity of the software systems we deal with. And lastly, it's the importance of understanding things at a deep level of detail. It's easy to look at that picture of the tractor and the air seeder and say that there's only two things, that there's only two kind of high-level systems there, two high-level use cases. But it's when you start to look at each of those and you start to literally break each part down and start to put it back together that you realize that it isn't just a tractor and an air seeder, that there's some 40 different subsystems there. And that's the part of the principle-based architecture and design approach that's been used for building the case of the use cases in the original did-uri-spec webcast, and using that to drive the design and architecture of the grammar itself. So thank you for your time for the last 35 minutes. listening to this presentation. I hope you understand the relative positioning of URIs created with the did-uri-spec and did URLs created with the ABNF, did-ABNF notation. It's not an either-or situation. The did-uri-spec completely covers and goes way beyond what the did-ABNF notation is capable of expressing. But given that there's a high level of capability, a high level of compatibility, and I highlighted a particular coexistence scenario where you can think of did-uri-spec URIs as being sort of higher level, easier to understand expressions of what document is to be returned by a resolver, and think of did ABNF based URLs as being sort of a lower level expression or a more technical expression of exactly the same 4 use cases. Thank you again.